Hello everyone, welcome back. My name is Mr. Kovald, and in this video we're going to be looking at some rate data, and we're going to calculate or figure out what the rate law of this reaction is, the rate constant, and the initial rates. So let's get into this. So in this problem, we're given that the rate of the reaction between hemoglobin Hb and carbon monoxide CO was studied at 20 degrees Celsius. The following data were collected with all concentration units in micromoles per liter. A hemoglobin concentration of 2.21 micromoles per liter is the same or equal to 2.21 times 10 to the negative 6 moles per liter. Why? Because micro is the what do you call it? The multiplier. The multiplier for micro is 10 to the negative 6. So 1 micro, whatever, 1 microgram is 10 to the negative 6 grams. 1 times 10 to the negative 6 grams. So 2.21 micromoles per liter would be 2.21 times 10 to the negative 6 moles per liter. Okay, because 1 micromole is equal to 10 to the negative 6 moles. Okay, so they're giving us this data here based on the reaction of hemoglobin with carbon monoxide. And we're asked to answer 3 questions. So the first one is determine the rate law. So when we're determining the rate law, we need to compare the concentrations and the change in concentrations depending on the initial reaction rate. So we look at the concentrations they give us, we look at the rates, the initial reaction rates that they give us using the initial concentration. So the 0 here, the O means initial. So here we're given initial amounts or concentrations in hemoglobin. Here we're given initial amounts of CO, carbon monoxide. And then based on these initial concentrations, we have the initial rate of the reaction. So we want to find the rate law. The way we do that is we isolate two of the trials here. So we have trial 1, 2, and 3 here. And so such that we're going to isolate two of them so that way one of the reactants is held constant. So for example, you'll notice that these two trials here, carbon monoxide has a concentration of 1 each, but you'll see there's a change in the concentration of hemoglobin. So we can compare these two and look at how the effect in the initial concentration of hemoglobin affects the initial rate of the reaction. We can ignore the carbon monoxide because that's held constant between these two trials. Now, for carbon monoxide, we can look at these two trials and see, look, if these two trials are different for carbon monoxide, but for hemoglobin concentration, it's the same. So we could use these two to figure out the relationship between the change in the concentration of carbon monoxide and how that relates to the initial rate. Now, there's a couple ways you can do this. First way is you could eyeball it and figure out what the relationship is. So let's go ahead and write out our generic rate law. So the rate law for this reaction would be the rate, whatever the rate of the reaction is going to be equal to the concentration. Oops, I forgot one thing. Is going to be equal to the rate constant K times the concentration of hemoglobin to some power x multiplied by the concentration of CO raised to the power of, say, some power of y. And so this is your kind of generic rate law for this reaction. And what we're trying to figure out for part A, right, we're asked to determine the rate law. we need to figure out what x and y are. So k we'll figure out in a moment. That's the next question. Calculate the value of the rate constant. The rate constant is k, but you want to figure out what the powers are here, what these exponents are for x and y. So that's what we need to figure out. So we need to isolate these two. So we're going to look at the data. Notice that the carbon monoxide is the same. We're going to put this data into the reaction, right? But we'll get to that in a moment, because I was saying, well, you could just eyeball the data and figure out what these x and y is just by looking at the data. So if you look at these two here, you'll see that this is constant, so we ignore this, and we're only looking at the change here and the change here. What you'll notice is that this differs by a factor of 2, right? So 4.42 is double 2.21. So I'm doubling the concentration when I go from trial 1 to trial 2. Now, if the concentration doubles between the two concentrations, we can look at how that affects the initial rate of the reaction. So you'll see here that I have 0.619, and then here I have 1.24. And if you look at that, well, double 0.6, if I multiply 0.6 by 2, that becomes 1.2. I have 1.24. So this is about double, right? So if I double the concentration of hemoglobin, that's going to cause the rate to double as well. And you see that there's that one-to-one relationship. If I double one, then I double the other. That indicates that your power for hemoglobin is a 1. This is a first order rate with respect to hemoglobin. So with respect to hemoglobin, it's first order. That means that the power is a 1. So anytime that you change the concentration of something and you get the same change in the initial rate of the reaction, that's going to be first order, and the power is going to be 1. The exponent is going to be 1. So if I was to triple the amount of hemoglobin, that would triple the amount of the rate. The rate would triple as well. If I quadruple, if I multiply by 4, if the difference between these two was a factor of 4, then the difference would be a factor of 4 there. That means it's first order. So whatever factor you see here, if this is double and this changes by the same factor, that's first order, and that's exactly what we see here. So I'm doubling between this one and this one. I double the hemoglobin concentration, and you'll notice that the initial rate doubles as well. Therefore, it's first order. So I can write that down as rate is equal to K, and that would be HB to the 1 power. Now, that's one way you could do it, but you could also do it mathematically and solve it for sure and see and show you that way. So let me show you how you do that. So in this way, I'm going to take these data points, I'm going to take the data here and plug it into the equation twice. So I'm going to take the rate. What's the rate? 0.619. So I'm going to take 0.619 is equal to K, don't know what K is, multiplied by the concentration of HB. What's that? 2.21. So I'm going to put that in. So we'll put in 2.21. And then we have for the carbon monoxide, that is going to be 1.00. But don't forget, we have X here, so we have to put the X. And then Y is, that's going to be carbon monoxide, so that's 1.00 Y. And then we do the same thing for our next one. So we're going to plug everything into the rate equation here. So here, same thing. So we have 0. So this time it's got 1.24 for the rate. So 1.24 for the rate. That's again equal to K times. And then for the hemoglobin concentration is going to be 4.42. So 4.42. And again, X. And then this is 1.00, 1.00, and then Y. So here's the two forms. I shouldn't say forms, but here's the equation plugged in with the two sets of data plugged in. So now what I can do is I can divide one equation by the other. So the easiest way to do is take the larger, right? So here I have a larger amount, divide that by this smaller amount. So I'm going to take this and divide it by this. So I'll rewrite this. 0.619 is equal to K times 2.21 x divided by or multiplied by 1.00 y. And so right away we can see that K is going to cancel out. And then we have 1.00 to the y on both sides, on the top and the bottom. So that will cancel out. And we're left with this divided by that, and this divided by that, up to the raised to the x power. So if we take this, we can get the factor that this differs by. So let's go ahead and calculate that. We get 2.00, let's say 32, I guess. And then that's equal to, and then since both of these are raised to the x power, then we can divide these two. So it's going to be, if we rewrite this, it would be 4.42 over 2.21 raised to the x power as well, right? So then if we divide this, obviously this is 4.42 divided by 2.21, that's going to be double. So then this is going to be equal to 2 to the x power. But notice here that 2.0032 is really close to 2. So if we round that, we get 2 is equal to 2 to the x power. Let me write that better. Well, what is the power of this 2? Well, it is to the power of 1, right? So if both of these have the same base 2, and this is to the power of 1, and this is power of x, and they're equal to each other, then this means that since the bases are the same, then the powers have to be the same. So x is equal to 1. And again, you could do this by taking the log of both sides, right? So if I do that, I can take the log of 2 to the 1 power is equal to log of 2 to the x power. And if I rearrange this, then the power can come to the front here. So it'd be 1 times the log of 2 is equal to, and then the x can come down. So it'll be x times the log of 2. And notice the log of 2 cancels out. So because I can divide both sides by log of 2, right? So then that cancels out on both sides, and then x ends up equaling 1. So you can do it mathematically and figure out what x is, or you can eyeball it and figure it out. Either way, it works. One way might be easier than the other. So if the numbers don't quite work out here, it might be easier just to do it this way. But if you're not sure how to look at this and look at the data, then you could always do it this way. You should always get the answer. Okay, so we have x is equal to 1. What about y? Well, we do the same thing for y. So for y, we're going to look at these two trials here. Why? Because for the hemoglobin, we're going to keep that constant now because we want to isolate the change in carbon monoxide because we want to find what y is. So now we're going to look at the change in the carbon monoxide and leave the hemoglobin to be constant, right? And so now we're going to look at how does the change in the concentration of carbon monoxide change or affect the initial rate of the reaction. And so again, notice here that you have a 1 to 3 change. So this is, you're tripling the amount of carbon monoxide. So this differs by a factor of 3. So what does that do to the rate? So if I triple the initial concentration of carbon monoxide, how does that affect the initial rate of the reaction? And you'll notice that this is about triple. So if I multiply this by 3, I get about 3.71, right? So if I triple the concentration of carbon monoxide, then I also triple the rate. So it's a 1-to-1 again, right? So tripling 1 has the same effect on the rate as well. So tripling the concentration of the carbon monoxide leads to having the same effect on the rate of the reaction, which means it triples the rate of the reaction. So that again means that it's a power of 1. This is a first order relationship, first order with respect to the concentration of carbon monoxide. So y would equal 1 as well. And oops, I forgot the 1. So, and we could do that. We could figure that out mathematically again. So let's go ahead and do that for those two trials. So again, the rate is going to be 3.71 for this trial here. So we'll do that one first. So we have 3.71. That's going to be equal to K times the concentration of the hemoglobin. So for this one, it's 4.42 to the X power multiplied by 3.00 to the Y power. And again, we'll do this one. So 1.24. So 1.24 is equal to K times, again, 4.42 X times 1.00 Y. And again, to figure out what this is, what the Y is, we're going to take the two equations here and divide them. We'll take the 3.71 divided by the 2.4, but notice again that K cancels out. And then here we have 4.42 to the X, 4.42 to the X, so that's going to cancel out. So we're left with 3.71 divided by 1.24 is equal to 3.00 to the Y divided by 1.00 to the Y. So let's go ahead and do that calculation. When I divide 3.71 by 1.24, I get 2.9919. So 2.9919 is equal to, and of course 3 divided by 1 is 3, and that's going to be 3 to the y. This here, 2.9919, is really close to 3. We could round that to 3. So basically we would have 3 to the 1 power is equal to 3 to the y. So since the bases are both 3, y should be an exponent. Since 3 is a base for both of them, then that means the y, the exponents should be equal to each other since the bases are equal and they're equal to each other. So, but again, we could do the log. We could take the log of both sides. So the log of 3 to the 1 power is equal to log of 3 to the y. So the exponents can come to the front. So that's going to be 1 times the log of 3 is equal to y times the log of 3. Divide both sides by the log of 3. So that cancels out. And we get 1 is equal to y. So y is equal to 1, just like before. So again, you can look at the data and eyeball it and figure out what the relationship is. So here, if the idea here, if you're looking at the data, is if the change in the concentration matches the change or the factor of the change in the initial rate, if they differ by the same factor, then that means that it's an order of 1, right? So it's a first order, which means that the exponent would be 1 for the concentration of that particular substance. If, for instance, if the factor is double, right? So if I change this by double, but that has here, it quadruples. So that means here the factor that changes here is 2. And then if the factor here was quadruple or a factor of 4, then the difference between 2 and 4 is a factor of 2. So that would be second order, right? So that means the exponent would be a 2, right? If you change the concentration here and it has no effect on the concentration of no effect on the initial rate. If the initial rate is the same, even though you're changing the concentration of this substance, that would indicate a 0 order reaction. So that means that your exponent would be 0 and it would fall out of the rate law itself. Right. So, but in this case, we found that the x and the y, the exponents here are both 1. So that means that this is the rate law for this reaction. Okay, now that's the first part here. So I'll go ahead and write that up here. So the rate is equal to the rate constant times HB, hemoglobin, to the 1 power multiplied by CO, concentration, to the 1 power. Now, I wrote it on the wrong part here. That's actually up here, but I'll leave it there. So the next thing we want to answer is calculate the value of the rate constant. So how do we do that? So now that we have this, what we could do is plug in all of the information given for any of these trials, and it doesn't matter which trial you use, just pick one, plug it all in and solve for K. So let's go ahead and do that. So we'll plug in this information here. So the rate is 0.619. So 0.619 is equal to K. And then we'll plug in the hemoglobin concentration 2.21 to the 1 power multiplied by the concentration of carbon monoxide. So that's going to be 1.00 raised to the 1 power. So this is going to be equal to K. Since these are ones, it doesn't matter. We're going to multiply 1 times 2.21. So that becomes 2.21 is equal to 0.619. And then we just divide by 2.21 on both sides. 2.21. So that cancels out. And then so K then is equal to 0.619 divided by 2.21. And when we calculate that, we get 0.28. 0.2800. So there's the rate constant. So we can add that to our rate law, right? So then the rate law would be equal to, so 0.2800 HbCO, the concentration of HbCO. So we found the rate constant. Now, for the last problem, they're asking what would be the initial rate for an experiment with the initial concentration of hemoglobin being 3.5 micromoles per liter, and the initial concentration of CO, carbon monoxide, being 2.00 micromoles per liter. Now, to do that, now that we have the rate constant, we can now take this equation here, just plug in the initial concentrations of the Hb, the hemoglobin, and the carbon monoxide, and solve for the rate. So let's go ahead and do that. So we're going to take our rate law here. So the rate is equal to 0.2800 multiplied by the concentration of hemoglobin times the concentration of carbon monoxide. So they gave us the hemoglobin and carbon monoxide concentration, so that's going to be 0.2800 times 3.5, so it's going to be 3.5. I believe that's a 0. Let me check. Yeah, it's a 0. So that's 3.50 there. Micromoles per liter multiplied by that of carbon dioxide, 2.00. So 2.00 micromoles per liter. And then all we need to do is multiply these together. And when we do that, we get 1.96. That's going to be micromoles per liter second. And that, ladies and gentlemen, is the rate of that reaction with those concentrations, those initial concentrations of carbon monoxide and hemoglobin. And that is it for this video. I hope you found this video helpful. I hope this answered your questions, or, I hope you found it entertaining. So if you found this, if you like this video, if you learned from this video, then by all means, like the video, share the video, hit that like button somewhere over there. Also, make sure that you subscribe to my channel. Help me out, please. I would really appreciate it. And hit that notification bell right up there. When you do that, make sure you click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic you would like me to cover, let me know. Put it down below. I would like to do that. Thanks for joining me and have a great day.